Business Intelligence. Today is November 14th, 2025. Okay, today we are going to look at a very important topic called dimensionality reduction, in which we will learn how to take a many-dimensional system, multi-dimensional system, and reduce this dimensionality to a number of dimensions that we choose and still be able to explain the most variability possible from it. Examples of multidimensional systems are examples of multidimensional systems. Are ubiquitous, are all over the place. The management system of a company has many dimensions because it has many KPIs. Or if you describe images, if you have an image of 4,000 pixels, you have 4,000 possible dimensions. Okay, so or videos. So if you want to understand the information within it in a fast way, like for instance your iPhone, when you put your face in front of your telephone and it recognizes your face, okay? Or when you send an image via, let's say, WhatsApp, maybe you've noticed your telephone makes a picture in a very high resolution, but when you get it from a friend via WhatsApp, the same image, the picture doesn't have the same high resolution. The picture has been reduced in its resolution, and it's because the dimensionality of the picture has been reduced in order to send it and allow for better, more effective data transmission. Okay, so whenever you use WhatsApp, you are going to use the methods we learned today. And the method we are going to learn today is called, it has a name, it has it's a standard method which is called principal component analysis. Okay, so in short, it can also be called PCA. P, C, and then A. Okay. All right. The definition of the principal component is a principal component, PC. Okay, I write just PC. Is the eigenvector of the covariance matrix. So the eigenvector of the covariance matrix, for this we need to know what the covariance matrix is. We will define everything. It's just a short reminder from statistics. But the intuition, okay? The intuition is the principal component is the direction in which variability can be best explained. Okay, so we look at the data set. Let's say, imagine just in 2 dimensions, okay, just to get the intuition of it. Imagine we have a data set with 2 KPIs, 2 dimensions, okay, so, and we observe these data points, okay? These data points are like products or something like that in a company. So the best direction to explain this data is the direction that reduces variability. And the best direction that reduces variability is intuitively this one, okay? So this is going to be our first principal component. I guess when we talk about, it should be the first, we're talking about the first principal component. Why? Because if we are like, put here a little person, okay, looking this way, the data will be best understood in this direction. Okay, so you see that if we look at this direction, most of the data are within very short range from the middle line, from this variability line. So the standard deviation of the curve associated to this direction is small. Okay, so variability is smallest in this direction. Okay, this is the intuition. Questions about this? Everything okay? Give me thumbs up, thumbs down, something. Okay, so nobody saying nothing. Good. Then let's look at the definition again. Definition of principal component is the eigenvector of the covariance matrix. Okay, we need to know what the covariance matrix is, of course, and then from there we can take it. Okay, so let me, I am sure you have seen this in the past, maybe in statistics, but the covariance matrix of a 3x3 matrix 3 by 3 matrix is defined as like this. Let's say A equals the variance of x, the covariance of x, y, covariance of x, z, variance of epsilon, covariance of epsilon z, variance of z, and this is a symmetric matrix, so we just go ahead and do this, and we have the covariance matrix. Okay, so imagine, like, for instance, this data come from a management system with 3 KPIs, and then we have calendar week 1, calendar week 2, calendar week 3, and so on. So we have the data here. And from there we take the values. Okay, so the variance of x, for instance, is the sum of x sub e minus x mean divided by n minus 1. The covariance of x and epsilon is x sub e minus x Mittelwert, y sub e minus epsilon Mittelwert divided by n minus 1. Okay. Is that cool? So this is the covariance matrix, and by getting the eigenvectors of it, we would get our system solved. Okay. So some of you might know what the eigenvectors of a matrix is, some of you might not. Let's do an example. So the eigenvectors, by the way, are calculated by, or the eigenvalues first. Calculated like this, and once we have the eigenvalues, we go and we solve the eigenvectors. And these eigenvectors form the principal components. Okay? But this is just a theory. Let's make some example with numbers that you can chunk and you can visualize and so on. Sample for 2 KPIs. Imagine we have KPI number 1. It's cost per unit. Okay, we have 4 weeks of data, 17, 19, 23, and 22. And KPI number 2 is the revenue okay, and which could be 34, 41, 46, and 45. Okay, and this is what we are going to call x. This is what we're going to call y. All right. So in this case, you don't need to standardize, you don't need to norm, because the range in which the data move or behave is pretty pretty similar, so we don't need to make a normalization or standardization. You can do it, but not necessary. So first we calculate the covariance matrix. For that we know we need first we need the mean value. Okay. For y and for x, and then for y, 34 plus 41 plus 46 plus 45 divided by 4 is 41.5. Okay. So the variance of x is 17 minus 20.25 square plus 19 minus 20.25 square plus 23 minus 20.25 square plus 22 minus 20.25 square divided by 3, which will give 7.67. The variance of y is 34 minus 41.5 square plus 41 minus 41.5 square plus 46 minus 41.5 square plus 45 minus 41.5 square divided by 3 equals 29.67. Okay. Once we have that, we can go ahead and calculate the covariance matrix, or the covariance, sorry, which is 17 minus 34. No, sorry, watch. 17 minus 20.25 times 34 minus 41.5 plus 19 minus 20.25 times 41 minus 41.5 plus 23 minus 20.25 times 46 minus 41.5 plus 22 minus 20.25 times 45 minus 41.5, and this yields divided by 3, this yields 14.5. So that our covariance matrix equals 7.67, the variance, then 14.5, 14.5, and 29.67. Okay, so far, any questions? Is everything okay? Can you follow? I don't know. Some reaction would be nice. Okay, so now we have the covariance matrix, but this is not the end of the story, because we are aiming for the eigenvectors of the covariance matrix. So we need to find the eigenvectors of this matrix. And this is done by calculating the determinant of A minus lambda times I equals 0. Okay, so this is the determinant of (7.67) minus lambda 14.5, 14.5, 29.67 minus lambda equals 0. Okay, the determinant of this is 7.67 minus lambda times 29.67 minus lambda minus 14.5 square equals 0. And this is 7.67 times 29.67 minus 7.67 plus 29.67 times lambda plus lambda square minus 14.5 square times 0. Okay, this is then lambda square minus 37.34 lambda plus 17.32 equals 0. Here you would use the known formula for it. It's called, in Germany, it's called Mitternachtsformel. 37.34 square minus 4 times 1732 divided by 2. This delivers two values of lambda. Lambda 1 equal 36.87. Lambda 2 equal 0.97. Sorry, 0.47. Just entering the values there. Okay. How this is solved is known. If you have ax squared plus bx plus c equals 0, x is minus b plus minus square root of b squared minus 4ac divided by 2 times a. This is known for a long time already for you, I hope. This you have to know, actually. Okay, so far any questions? No? Then if you take, let's say, lambda 1, we're not ready yet because we are looking for the eigenvectors, not the eigenvalues. So if you take lambda 1, which is 36.87, this will take us to the equation a times v1 equals lambda 1 v1. Okay, this can deliver us the first eigenvector. Entschuldigung. So here we have the matrix 7.67, 14.5, 14.5, 29.67. Here we have v11, v12. Then the first eigenvalue, 36.87. And then v11, v12. So by solving this equation, we get, or these two equations, we get 7.67 times V11 plus 14.5 times V12 is equal 36.87 V11. The second equation is 14.5 times V11 plus 29.67 times V12 equals 36.87 times V12. Okay? Meaning that you get, like from the first one, V11 is equal to 14.5 divided by 29.2 V12 equals 0.49 V12. Okay. If we make, and this is an important step. We always make the first element 1. If we make the first element 1, then the second element is 1 divided by 0.49, which is going to be around 2. Wait. 1 divided by 0.49 equals 2.04. Okay, so the first eigenvector has elements 1 and 2.04. Okay. For the second eigenvector, it was 0.47. We do exactly the same. A times V2 equals lambda 2 times V2. So 7.67, 14.5, 14.5, 29.67, V21, V22, 0.47, V21, V22. Okay, so the first equation is 7.67 times V21 plus 14.5 times V22 equals 0.47 B21, B21, see? And then 14.5 times V21 plus 29.67 times V22 equals 0.47 times V22. Putting those both together, we get that V21 equals 14.5 divided by minus 7.2, V22 equal minus 2.01 V22. So the second, if we make V21 equal 1, then V22 is minus 1 divided by 2.01, and this equals 1 divided by 2.01 in minus. This equals minus 0.497. Okay, so the second eigenvector we're looking for is 1 and minus 0.49, sorry. Okay. Good. Is this understood? So these are the two results. And now, yeah, one question. What? Yeah, because here we have a minus. Okay. Yeah, so these are the two results. Now let's learn what they mean, because it's important to learn how to interpret the results, not only just be like a blind calculator, especially for people doing management. Okay, so the two let's look at the data first. So if we represent the data like this, let's say we have here x and y, and we represent the data like where do I have the data here? Somewhere here. So we have, this is 5, 10, 15, 20, 25, and then 5, 10, 15, 20, 25, okay, something like that. Or say this is 10, 20, 30, 40, 50, and this is 10, 20, 30, 40, and 50, okay. And I represent the data. The first data is 1734, so somewhere here. The second data is 1941, somewhere there. 2346, 2346, something like this. And 2245, so also going to be like something like this. Okay, I don't know. The scale might be a little bit different, but this is just the way it approximately would look like. Okay, so we can expect something like going on in this direction, somewhere like this, right? Okay, let's look at our vectors. Let's see if that is the case. So the vector 1 to 2.04, the first eigenvector, is going to be our first principal component. It's going to be the most significant direction of the data. Where does it go? Well, this vector goes like, it moves 1 in the x and 2 in the epsilon. Okay, so like this. If we continue with that direction, what do we get? Oh, magic. Okay, so it moves 10 in one direction and then 20 in the other. 1 to 2.04. And like magic, you see, this direction is exactly the main direction in which the data have been moving. So this is our V1, which is our principal component 1, which explains most of the variability. Why? Why do we know? Because here we have 36 to 0.47. So 36 is way bigger, way higher. Okay, so if we want to know how much variability we are explaining, what do we need to do? Well, we need to do what we have. Lambda 1 is 36 point something like 36.87, and lambda 2 is 0.47. Okay, So the amount of percentage of variability explained by lambda 1 is going to be 36.87 divided by 36.87 plus 0.47 times 100. Okay, let me do it again. I'll write it down bigger because it's important. So let me write it again. The amount of variability explained by each principal component is given by the eigenvalues. Okay, so the amount percentage of variability explained by the first principal component V1 is going to be 36 or better lambda 1 divided by the sum of all lambdas times 100, which is 36.87 divided by 36.87 plus 0.47, right? Yeah. And this is going to be times 100. This is going to be a lot. It's like 99 or something. 36.87 divided by 36.87 plus 0.47 is going to be 98.7%. The amount of variability explained by the second eigenvector is the same, lambda 2 divided by the sum times 100. Okay, so 0.47 times 100 divided by 36.87 plus 0.47 equal 1.3 or something. It's the other 100 minus the other. Okay, this is super important result. Make sure you engrave it in your brains. When you are a leader in next couple years, in 2, 3, 4 years, you will be managing teams. You will have a hell of a lot of information to manage. You always want to reduce the amount of information without losing decision power. So you want to reduce the dimensions without losing explainability. And in order to achieve that, one of the best, fastest algorithms is PCA. By the way, the second eigenvector is not so important. So you could manage this system with just one eigenvector, because with just one KPI, with one eigenvector, you would get 98% of the variability explained. So you're reducing from 2 to 1, which is a lot of reduction. It's 50% reduction. You would hit 98.7% of variability explained. Okay. The second eigenvector is 1 minus 0.49, and this is guess what? This is just perpendicular. Okay. moves like that, perpendicular, and this eigenvector does not explain as much by far. V2, okay, this is the second principal component. Data are organized around the first principal component. Of course, reality is not always so nice, okay? Maybe sometimes you just explain 70% or something with the first eigenvector, that's when you get 2 or 3, but still, you get the point. Question, go ahead. Oh, I'm drawing the vectors, okay. Yeah, if you have never seen it before, then it's not so simple, but in reality it's easier, like taking a shit, okay? Look at this. If you have the vector, let's say I have the vector, what numbers you want? Between 0 and 10. Hello? You don't know, tell me. Decide. 1, 3.5, like this. Very good. So this vector is like 1, it moves 1 in the x, okay? It's going to be moving you 1 in the x and 3.5 in the epsilon. 1, 2, 3.5. So you go ahead and you drive. If you want to move in that direction, you move 1 in the x and 3.5 in the vertical. All right? Yeah. So that's the way it works. No problem. So it's very easy, but if you don't get it explained with a graphic, then math is abstract. So always, whenever you are you have some teacher or somebody explaining math, demand that the person explains it with pictures. You have to demand it, okay? Because they will not notice. Anyway, so this is the way you paint the vectors, okay? Of course, it's the same in 3 dimensions. In 4 dimensions, you cannot paint it. How to draw a vector. Okay? So another question that I'm going to ask you, if, knowing this, no, I will not. I will not. This has to do with the linear, how do we call it? Linear regression from the other day. So with principal components, you can do sort of a linear regression as well. But I don't want to mix up the concepts, so I will not say anything on that direction. So any questions on this? As I said, this method is used whenever you send a picture via WhatsApp. Okay, like imagine you have a picture, just as a closure. Imagine you have like a nice picture here, okay? You have taken this picture. If you send it via like WhatsApp, and you are reducing from 310 to 310 dimensions, which is the number of pixels you have. You might send this image also with this so that it's recognized using like only 20 PCAs. Okay, and by using that you would still send the same image with less resolution. Okay, this is what, or you maybe you've heard of zip. You've heard of zip data compression. This is the principle used behind data compression. So basically, without PCA, we would not be able to be talking right now. Okay, on the internet with video and everything, it would not be possible. Super important. Make sure you understand it well, you use it, and you give yourself new data. Okay, like I gave you an example. Give yourself new numbers and chunk them. Okay, do the math yourself. Any questions?